Thank you, Katie. My name is Larry Hawkins, and I'm Director of Technical Marketing and Systems for Richardson RFPD, an RF-focused technical distributor and system solution provider. I'm with Elliot Nelson, Principal Design Engineer for NextGen RF Design, an RF design services company. And we're going to be talking to you about a MATLAB and Simulink toolbox for a 30 megahertz to 6 gigahertz RF SoM. Before we talk about the MATLAB and Simulink toolbox, let's talk about the RF SoM. The two main components of the SoM are the analog devices Navasa and Xilinx UltraScale FPGA. The BitePipe was designed to facilitate evaluation of Navasa, prototyping of RF communication systems, and for integration into a wide array of products. There are three different parts in the Navasa family. The ADRV9002 is a full-featured device. The ADRV9004 is the same as the ADRV9002 without DPD. And then the ADRV9003 is a 1x1 version of the ADRV9004, i.e. a 1x1 version of the ADRV9002 without DPD. As stated, all parts go between 30 megahertz and 6 gigahertz and have the same RF performance specifications and functionality. Current parts in stock use the ADRV9002 or full-featured transceiver. The ADRV9002 has two transmit channels, two receive channels, and two synthesizers that can be muxed to any combination of the transmit and receive channels, allowing it to be used for FDD or TDD applications. Or you could even use one of the receive paths as a sniffer to see which frequency bands are not being used while the rest of the system is turned off, and then switch the whole system to the empty frequency band. It has various low-power modes and the ability to do fast frequency hopping and DPD. I believe the first open market digital pre-distortion that works for very narrowband applications. It also has a SPI or LVDS digital interface, allowing it to be used with an inexpensive processor or FPGA. Navasa also has various digital functions like digital down converters, FIR filters, and multiple parts can be synchronized together for MIMO-type applications. So with Navasa, you get state-of-the-art performance, RF system calibration you no longer need to implement in the processor or FPGA, reducing the cost of your processor or FPGA, and system features that allow you to customize the performance for your particular application. And all of this in a very small 12mm by 12mm BGA package. Many modern-day systems need to be everything to everyone, especially those used for critical communications. They need to be high performance and yet run a very long time on battery power. They may need to use narrowband FSK modulated signals and then switch to a wider band QAM type modulation. They may need to switch frequencies very quickly or need to be at two different bands at the same time. They may even need to monitor a wide frequency range using very low power to look for other users in their frequency range of interest. What they all need is to put the right digital functions in the right place to reduce power, complexity, and size. All of these are available using Navasa. It's a perfect part for those looking to have high performance while reducing the size, weight, and power of their systems. The hardware design of the BitePipe SoM is not trivial, requiring expertise across multiple domains, including high-performance RF, power supply, and high-speed digital design. Combining these technologies into a highly integrated platform requires a significant engineering investment. The bipipe SoM facilitates lower engineering costs and shorter times to market, allowing developers to focus on adding value for their customers. Versions of the bipipe can include any of the Xilinx UltraScale FPGAs. We currently have a version with the XCU3EG in stock, and will soon have the XCZ-U2CG version. To go along with the transceiver and FPGA, the bipipe has 2 gigabits of RAM and 8 gigabits of flash memory, and all of this in a small 36.8 by 61 millimeter package. I'll turn the time now over to Elliot, who'll talk about the MathWorks tools that are available with the bipipe.
Thank you, Larry. Today I'm going to talk about MATLAB and Simulink for the bipipe RF SoM. We will start with an overview of the bipipe software development kit and discuss the bipipe toolbox for MATLAB and Simulink. We will finish with an example modem using HDL coder. The bipipe software development kit provided by NextGen RF Design is a collection of software and programmable logic examples to help users evaluate the SoM and ultimately develop their own product. The following block diagram gives a high-level overview of the software components. There are 3 main software components, including the application processing unit, consisting of a quad-core Cortex-A53 processor, the real-time processing unit, consisting of a dual-core Cortex-R5 processor, and the programmable logic. The bipipe SDK is available on NextGen RF Design's GitHub page. The SDK consists of source code and documentation for several examples targeting the application processing unit, the real-time processing unit, and the programmable logic. Also included is the bipipe toolbox for MATLAB and an HDL coder example, both of which we'll be discussing today. The folders under the source directory are a collection of examples and libraries, generally targeting a specific processor or the programmable logic. Each set of source files are for the most part independent of one another, and they can be combined in a variety of ways to create a full solution. Each source folder contains source code, documentation, and build scripts for generating the executable. The following highlighted modules generally target the application processing unit. The ADRV9001-SDK module includes build scripts and source code for duplicating the transceiver evaluation software provided by Analog Devices. We will touch on this module later when discussing the bipipe toolbox. The following highlighted modules shown here target the real-time processing unit, typically running bare metal or FreeRTOS applications. The RFLAN QPSK component will be used as part of the HDL coder example. The following modules are targeted towards the programmable logic. The QPSK module includes the Simulink HDL coder example we will be discussing in a moment. Before jumping into the HDL coder example, I'm going to give a quick demo of the bipipe toolbox. The bipipe toolbox includes 3 distinct modules. The RFLAN and the ADRV9001 modules are MATLAB classes that interface to the bipipe software through a serial connection or Ethernet connection. These classes can be instantiated in MATLAB and run independently using custom scripts developed by the user. The bipipe app is a MATLAB application that interfaces to either the RFLAN or ADRV9001 class, depending on the software programmed in the bipipe. We are going to start by demonstrating the bipipe MATLAB application connected via the ADRV9001 MATLAB class. This requires the bipipe application processor to be programmed with Ubuntu and the programmable logic programmed with sources built from the Analog Devices ADRV9001 SDK. Since we won't have time to go through the build process today, we will start with a pre-programmed SD card. Okay, I'm going to switch over to sharing my screen now. Alright, hopefully you can see my screen okay. What you see here is the MATLAB bipipe application. I will walk through some of the features real quick. The connection type can be ADRv9001 server or RF LAN server. The selection depends on the software running on the byte pipe. The ADRv9001 server was developed by Analog Devices and comes with the ADRv9001 SDK. The server is a Linux application running on the byte pipe application processor. The server allows remote calls to the programmable logic for configuring and exercising the ADRv9001. The RF LAN server is more of a production type interface that interacts with the programmable logic and Cortex-R5 real-time processor. The ADRv9001 server is optimized to expose every ADRv9001 API, but comes at the expense of complex programmable logic footprint. The RF LAN server offloads the programmable logic using the Cortex-R5, but does not provide the same level of API access remotely. The MATLAB app supports both with slightly different features. For this demo, we are going to use the ADRv9001 server, and for the HDL coder example, we will use the RF LAN server. I am going to power on the byte pipe, and as you can see from the command line interface, it is booting. Before we connect to the byte pipe, we need to generate settings from Analog Devices transceiver evaluation software, or TESS. Whether using the ADRv9001 server or the RF LAN server, or even your own custom application, this step is required. The TESS software serves as a configuration tool for generating all the necessary register settings based on the user's configuration. Since we're using the ADRv9001 server, we can export the settings by generating MATLAB sample code. This allows our MATLAB application to configure the device. If we were using the RF LAN server, this step would be slightly different. In the case of the RF LAN, the test-generated settings are embedded in the RF LAN firmware. The Cortex-R5 running the RF LAN firmware is responsible for configuring the ADRv9001, and MATLAB simply interacts with the RF LAN API. In this case, however, since we are using the ADRv9001 server, the PC is responsible for configuring the ADRv9001, with very little interaction from the application or real-time processors on the byte pipe. This is why the ADRv9001 server is ideal for initial evaluation, whereas the RF LAN server embeds much of the control and is optimized for a production use case. We're going to configure the ADRv9001 for a sample rate of 7.68 megasamples per second and a carrier frequency of 2.45 gigahertz. We can then export the MATLAB settings to our workspace folder. And here you see the MATLAB generated code from TESS. You can close TESS and connect using the MATLAB app. After selecting connect, you can see it reads the device information from the byte pipe. Next, we can go to the Profile tab and select our previously exported configuration. You can see it loaded the files, and now we can select Write Profile. This takes some time because the PC is driving the entire process and individual reading and writing of registers. It starts by initializing the ADRv9001, followed by calibration, configuration, and priming of the transmit and receive channels. The last step is reading all the profile settings to display in the MATLAB app. Okay, here we have all the profile settings that were generated from TESS. We can see here our receive sample rate is 7.68 megasamples per second. Okay, now we are going to explore some of the transmit functionality. Before enabling the transmitter, we see the radio is primed and the carrier frequency and sample rates are correct. Next, we can enable the transmitter. Because we generated the initialization code from TESS, the transmitter was initialized to transmit a file. If we were using the RFLAN server, we could select our own file or waveforms to transmit. I will bring over my spectrum analyzer so you can see the result. I could change the transmitter attenuation, which is actually one of the few real-time parameters the ADR V9001 server allows to be changed. Okay, now we can go to the Receive tab. We see the receivers are primed and we can enable them. I have the BytePipe TX1 and RX1 ports connected through a combiner to a spectrum analyzer and a signal generator. If I turn on the signal generator, you can see the BytePipe receives the same signal as the spectrum analyzer. If I shut off the signal generator and turn on the ADR V9001 transmitter, you can see TX1 and RX1 are connected through an external loopback. Okay, the last thing I want to show is the filter tab. Here I can read one of the 4 coefficient sets for either the receiver or the transmitter. If I want to change the filter response, I can use the wizard to create a set of coefficients and write them to the device. This concludes our demo of the BytePipe MATLAB Toolbox. All source code and documentation can be found on NextGen RF Design's GitHub page. Next, I will be demonstrating a MATLAB HDL coder example for the BytePipe. The first thing I'm going to do is open MATLAB and browse to the BytePipe SDK source folder. I can then open the QPSK folder and open the Simulink model and example script. The one thing I should mention is this example is purely based on a MATLAB example named COM HDL QPSK TXRX. Documentation can be found by searching MATLAB help. As you can see, this brings up the documentation for this example. We could have created our own example, but there's a lot of value in demonstrating just how easy it is to get a MathWorks example up and running on the BytePipe SoM. If we scroll through the documentation, it clearly walks users through step by step. We are going to execute the same demo, but with the added steps of running this example on the BytePipe SoM. As you can see from the Simulink model, we have a transmit block, a channel model, and a receive block. If we look inside the transmit model, it is a fairly basic QPSK transmitter, as we would expect. Input bits are packetized, scrambled, modulated, and filtered to produce IQ samples. The receiver blocks are slightly more complicated. Automatic gain control is followed by matched filtering, frequency and time synchronization, demodulation, and finally descrambling and packet decoding. The input signal is IQ samples, and the output signal is data bits with start and end strobes marking the packet boundary. We can open the plot windows and run the simulation. The simulation sends 10 packets, each 2,240 bits in length. The plot in the lower right is the output from the correlator used for frame synchronization. We can see that the peak corresponding to each of the 10 packets. The default simulation applies a time offset, symbol frequency offset, carrier frequency offset, and carrier phase offset, along with white noise. These effects are clearly seen in the constellation plots before and after symbol and carrier synchronization. If we run the verification script, the simulation is repeated, indicating the number of packet errors and bit errors, which you can see is 0. To generate the HDL code, we can start by opening the transmit model and navigate to the HDL code toolbar. Here we will select code generation for the TX model and launch the Workflow Advisor. We need to set the synthesis tool and target device to match our BitePipe board. Instead of creating the project folder next to the source files, I like to change the directory to my temporary workspace folder. That way I can delete this in the future and not accidentally delete any of my source files. The next thing we want to do is run the HDL code advisor to check our model before generating the HDL. Okay, so you can see we have 6 warnings. We can go through each of these warnings and even have the advisor fix any potential issues. Now it's going to give me an error. This is because the previous warning I had the advisor fix had to do with the model name. The advisor changed the name to be compatible with the HDL code generation. To finish going through the checks, I need to close the model advisor and reopen. Okay, so we have 2 warnings yet. This one here is indicating I should change my reset to synchronous, which I will do. Next, we can check our HDL code generation settings. I prefer Verilog, so I will change it to that. I also know the ADRV 9001 HDL module we are interfacing to has an active low reset, so I will select this. It also happens that the clock coming from the ADRV 9001 is running at a factor of 2x the sample rate. Now we can set our code generation settings to include the RTL and test bench. Normally I generate a project and invoke synthesis from here, but to save time I will only have it create a project. Okay, it has finished with no errors. Now we can open the Vivado project. And next open the Verilog source files, and as you can see we have a packetizer, scrambler, modulator, and pulse shaping filter, just as we would expect. We can now package this project as a custom IP. That way, when we go to build the HDL for the byte pipe, which includes ADRV 9001, we can instantiate this module as our transmitter. Next, we can build the receive HDL in the same way we did the transmitter. While that is running, we should talk quickly about the sampling times. When we were running the HDL advisor, one of the suggestions was to turn on the timing information. This is why the model changed colors. If we turn on the timing legend, we can see the different colors correspond to different sample rates. This model was originally set up for a sample rate of 7.68 megasamples per second with 4 samples per symbol. As you can see from the timing legend, red represents a sample time of 130 nanoseconds, or 7.68 megasamples per second. The HDL oversamples each symbol by 4 samples, resulting in a symbol rate of 1.92 megasamples per second, which is represented in blue. With 2 bits per symbol, the data rate equals 3.84 megabits per second, represented in green. If we look at our model, we can see that the bits going into the transmitter and coming out of the receiver are green, representing 3.84 megabits per second. The IQ samples coming out of the transmitter and going into the receiver are red, representing a sample rate of 7.68 megasamples per second. This is all relative to whatever clock we decide to hook up in the HDL. I know the ADRV 9001 module supplies me with a clock twice the sample rate, which is why I selected an oversampling of 2x. I also set my clock to 15.36 megahertz when generating the HDL to use for timing analysis. Okay, so the receive HDL has been generated, but I didn't run create project yet, so we'll do that now. While the receive HDL project is being generated, I can get ready to generate the main HDL project. The good news is we already have the source code and build scripts for this as part of the BytePipe SDK. To build the project, we need to launch Cygwin. I don't want to start this until all the receive IP is done, but I can make sure the other IP has been built. It looks like the receive HDL project is finished. We can launch Vivado and package it like we did for the transmitter. Now that the IP has been packaged, we can finish creating the main project by launching the HDL build script. This will use the previously generated transmit and receive IP modules that we created. While it is building, I can open the project in Vivado to monitor its progress. The following shows the block diagram of the HDL that will be programmed into BytePipe. At this point, to save time, I'm going to kill this process and open a previously compiled project so we can review. Actually, I have a few projects with some slight modifications that I did for testing. The following project connects the transmit and receive modules directly together, ignoring the ADRV9001. I did this for testing of the HDL components to avoid any issues that may arise when configuring the ADRV9001. You can see from the diagram the QPSK transmit input is connected to the DMA. The IQ output is connected directly to the IQ input of the receive module. And the output of the QPSK receive module is connected to the receive DMA. I added an integrated logic analyzer to monitor the inputs and outputs of each module. The following is a closer look at the receive block diagram and the instantiated QPSK receive module. The output data going to the receive DMA is 32 bits, allowing me to map the receive bit interface along with the packet start, end, and sync strobes. This diagram shows the transmit circuit, including the instantiation of the QPSK transmit HDL. Here I connected the least significant bit from the DMA to the input of the transmit HDL. The following shows the signals captured on the logic analyzer. The transmit bits on the top are coming from the DMA using the RF LAN interface. A simple pattern was created and continuously streamed to the transmit HDL. The second two waveforms show the HDL generated IQ waveform, and the bottom 5 signals show the receive bits, the start, end, and sync strobes. By triggering on the end strobe, we can see the receiver temporarily pausing to capture frame synchronization. followed by a start strobe and received data matching that of the transmitted data. In this scenario, the transmit DMA is continually streaming transmit bits, resulting in the QPSK transmit HDL to continuously stream packets back to back. The following shows the Vivado project summary. The project without optimization consumes roughly 20% of the BytePipe programmable logic resources. The following shows the resource utilization for each module relative to the available resources on the BytePipe. The transmit module consumes the least amount of resources, while the receive module consumes roughly 6% of the logic resources and 25% of the DSP slices. These numbers can be greatly reduced by increasing the clock and oversampling factor. For example, increasing the clock to 154 MHz would decrease the DSP slice usage to below 2.5%. Here we can see the distribution of resources for the receiver, with the majority of resources dedicated to frequency and time synchronization. The receiver root raise cosine match filter consumes roughly 5% of the DSP resources. The following shows the receive and transmit modules connected to the ADR V9002. We can see the QPSK transmit module receives input data from the DMA and outputs IQ samples to the ADR V9002. The QPSK receive module takes input samples from the ADR V9002 and outputs data bits and strobe signals to the receive DMA. This project results in almost identical resource utilization as we would expect. To test the RFLAN QPSK demo, we generated the RFLAN firmware running on the Cortex R5 processor using the Eclipse-based Vitis tool from Xilinx. This is a fully embedded workflow with examples provided in the BytePipe SDK. The ADR V9001 profile that was exported from tests in the previous steps was used as generated C99 code. The RFLAN PHY layer provides abstraction, allowing for a simple transmit and receive API that supports various RFLAN projects, including streaming of IQ data or data bits to and from the HDL, like in this example. To interface to the BytePipe, the RFLAN was compiled to use a simple command line interface connected directly to a serial port. We could have compiled the Linux image to run on the application processor, allowing for remote calls to the RFLAN through the Linux bash terminal or a socket server, which implements the RFLAN server, allowing us to connect to the BytePipe MATLAB application. The following shows the bare metal CLI commands related to the PHY running on the Cortex R5. If we do a file list of the Cortex R5 file system, we see a file named txpattern.csv. This is the file containing the specific transmit bit pattern we used in our testing. Here we enabled continuous stream of the TX pattern, followed by reception of 40 bits. The least significant bit of the receive word, as mentioned before, is the data bits, with bit 1 being the start strobe, bit 2 the end strobe, and bit 3 the sync strobe. We can clearly see by looking at the least significant nibble, the pattern being received matches that of what is being transmitted. Here's a spectrum plot at the output of the BytePipe transmitter. It is roughly 2.5 MHz wide, as we would expect. Although this example implements a basic scrambling algorithm, the underlying transmit pattern results in some additional spurious that would likely be cleaned up with a more robust scrambling method or random data. This concludes our demonstration of the BytePipe MATLAB Toolbox and Simulink examples. For additional information, please see NextGen RF Design's GitHub page. And with that, I will turn it back to Larry for some final remarks.
Thank you, Elliot. As a preview, we'll soon be releasing some RF front ends to go along with the BytePipe. These boards can be used in the place of the breakout board that allows you to evaluate the SoM. Richardson RFPD's radiocarbon design accelerators consists of 3 designs, covering frequency ranges from 1.35 to 2.7 GHz and 4.4 to 5 GHz. They include a full RF front end, transmit and receive, that can be used in TDD or FDD modes. Output powers are 40 watts or 20 watts PSAT and 2 watts or 1 watt linear, assuming a 10 dB peak to average signal. The boards can be used with any transceiver that has DPD through SMA connectors, but was designed specifically to work with the BitePipe SoM and ADR-V9002 eval board. We believe that customers working on military communications, SATCOM, troposcatter, non-line of sight backhaul, and 5G applications should be particularly interested in these boards, although they can be modified to work in other frequency bands. We expect to have stock of the 4.4 to 5 GHz version in before June. Katie, that's all we have for today. We'll let you open it up for questions now.